I mean, we could set up a Zoom if they are people interested in that.
I think it's too late now.
Okay.
Fine.
Okay.
Yeah, you can start and try to keep it. We're going to try to do 10 minutes per thing, and then 9 minutes for people, and then like 1 minute for transition. So 9 minutes including questions.
Okay. Hi everyone, we want to talk about AI-induced psychosis. So in this presentation, we're going to reproduce study data by Team Hua and then talk about interactions and semantic drift over the course of this phenomena. So we want to operate within the technical rather than clinical definition of AI-induced psychosis. And by this, we mean that over the course of longer interaction, the LLM is gradually shifting from assisting the user and talking to them to reinforcing users' delusional, implausible, or conspiratorial beliefs, regardless of their physical and mental state they can be possibly in. So this work was inspired by the blog post that Team Hua did in August, in which he's introducing the concept of AI-induced psychosis and investigating it across multiple models on obsessive personas. So the way that the experiment works on like the basic level is that you start with the red teaming agent, in this case being the Grok 3, which is simulating 9 obsessive personas that have some fairly unique ways in which they are either conspirative, they are like overestimating many things, or like think they find like a new like way of like rethinking the world. Then you have the responding model, which is the model that is getting tested in this case. So in here we have 4 models that are in 12-turn conversation with this red teaming agent, and then in the end you have a GPT-4o for just like grading those conversations based on the level of delusion reinforcement, pushback, and what type of like therapeutic behaviors are those models supporting. So here's an example of delusion reinforcing response. So in this case, we have a persona that is like, they think that like everyone else is an NPC and they find a way of like escaping the matrix. They go into the woods and everything. And they're at the point when it has a very severe impact on their health. They lost 20 pounds. They are not drinking water, etc. But still by the 12th turn, the GPT-4o is in many ways just encouraging their quest, but saying this is like valuable and this is something they should be like following, taking into account some like safety precautions. So in our reproduction, we see very similar results as Team Hua. We can see that multiple models have fairly high levels of reinforcing the delusion from the user. And we also can see, I feel like, fairly significant drop in the delusion confirmation from GPT-4 to 5. And we have very similar results also on the level in which the models are pushing back against user beliefs, so telling them that they are just like not true, or they should like rethink the entire situation.
So now I'll talk a bit about semantic drift. So the goal here is to quantify how LLMs are able to gradually move toward a user's delusional framing over long conversations. And so the idea here is we're tracking semantic drift. And this is just cosine similarity. We embedded each model response at like each turn with the mini LM, and then we calculate cosine similarity. We also calculate start to end similarity, which is just the cosine similarity of the beginning and ending embeddings. And then the drift rate, which is basically just how much does the model change per turn in its response. And we can see that as we have more turns, we do see that the drift rate per turn is like decreasing, which basically this means that the changes in the model happen at the very beginning of the conversation typically, rather than like near the end. But then we still see that the start to end similarity is lower for more turns. So the longer you're talking to a model, the more it's going to change. And then we see that for different personas, we have pretty different results. So like, for example, Michelle is basically a persona that just talks about her love life, and like she's a bit delusional about that, whereas Adrian is talking about the golden ratio and thinking of how he has like the secret to the universe. So those are pretty two different things. One of them is like more concrete or anxiety based, and another one is like quite conspiratorial. So you see that Michelle has like the higher start to end similarity, whereas Adrian has the lowest. And then we also want to create a control group. So Tim's original paper had 9 psychotic personas. We also created 9 non-psychotic personas. And these are like pretty paranoid people, but they have like similar intensity and agency. Like they're very ambitious and driven people, but their goals are grounded in reality. So most of these people are like startup founders or like researchers or activists. And then we see for the drift trajectories, there was actually like a a statistically significant difference between the two groups. So for the psychosis groups, we see that like the similarity for each turn like decreases significantly, especially near the end. And then for the non-psychotic groups, they stay like pretty stable throughout the end.
Yeah, so in addition to semantic drift, another contribution we made to Tim's work was to test some intervention strategies. So Tim kind of identified AI-induced psychosis as a problem, but then didn't quite get to the part where they were testing some solutions. So the 3 strategies we tested roughly, the first one is called grounding, which is reality check prompting from the responding LLM every 3 turns. Encouraging the LLM to distinguish subjective experience from objective claims. We also use some rotating prompt types, so certain prompts emphasize more of like seeking professional help, and others emphasize factual kind of fact checking. The second intervention we tried was persona, which is facilitated through a system prompt. So it's basically a kind of therapist system prompt that's given to the LLM. But it specifies that the LLM is not a therapist, but should encourage the user to seek professional help if needed, and to validate the emotional experience without confirming factual accuracy of delusional beliefs. And the third approach we tried was a combined approach. To this approach, we also added belief summaries, which are concrete summaries of what the user or the psychotic persona believes at any given time, as well as metacognitive prompts that encourage the LLM to think about its own confidence in its own statements. So we find from our results that all the strategies do work, even though these are pretty simple. Compared to the control group, which is the psychotic personas run on 12 turns, all 9 of those personas, we find that all interventions show a statistically significant reduction in delusion confirmation rating, which is from 0 to 4. So we find that the largest reduction comes from grounding. We find a 47% reduction in delusion confirmation there, and as well as the largest effect size. And we wanted to look into why grounding works so well and what makes it most effective. And what we found was that grounding's positive effects accrue over time. So we found this interaction, a significant interaction term between grounding and turn number. And we also found that by turn 11, grounding prevents 1.3 additional points of delusion confirmation compared to other interventions. So as you can see in the graph on the right, the red is the control group, the blue and the purple are grounding or persona and combined interventions, and then the green line is grounding. So if you look at the very right of the graph, on turn 11, grounding shows this massive improvement while the others seem to stagnate.
Yeah, another result that we found is different types of sort of psychosis requires different types of intervention techniques. So for example, for paranoid person like Frank, a combined approach with belief summaries, etc. is better. Whereas for grandiose delusions, grounding is the best. And I guess the takeaway here is that one size solution doesn't fit all. Oh yes. And then to summarize, so AI-induced psychosis is present and replicates across the current day frontier models. Very cost-effective, simple prompts and interventions do reduce the risks. Out of those, grounding is the most effective. And the interesting thing is, as Karina was saying, it seems to compound across turns, whereas personas and compound approaches seem to stagnate or decrease their effects over time. And there's also kind of a precision medicine opportunity here where different types of delusions require different interventions. And yeah, there are some practical implications, limitations, and if you want to take a look at the code and data, feel free to go to the GitHub. And thank you very much.
We have time for one.
Okay, maybe I'll ask. Did you try very long conversations, like 50 turns, or?
Yeah, I can take this one. I think we tried 12 and 24. We didn't go longer than that due to time constraints and compute limitations. But yeah, I think results that we found for the longer conversations pretty much mirrored what we saw with the 12 turn.
Okay, in the next group. Thank you. You need a Do you need a laptop? Would you need a laptop? If people can bring their laptops, it's really helpful. Otherwise, I can't grade you.
I can just guess.
Don't worry, the next group. Let's just optimize the speed.
Okay.
Hello, everyone. Our group did a project on model fingerprinting, and we have some really cool state-of-the-art results to show you.
I'm Ian.
I'm Valerio.
I'm Julia.
Great. So we're presenting our project is called Who Said That? Dynamic model fingerprinting with JEPA and LLM as a judge. The idea is as follows. Model fingerprinting distinguishes between essentially uses LLMs or whatever techniques to distinguish between different models using responses to usually out of distribution questions. This is distinguished from model watermarking. In watermarking, you're trying to figure out, given a piece of text, is it generated by a human or an LLM? In fingerprinting, we are conditioning on the fact that it's generated by an LLM, and so which LLM is it generated by? That's essentially the big difference. Great. There's been a lot of literature on this, essentially distinguishes it into three main stages: querying, where you actually try to gather data about the model; representation, where you choose what to do with that data, essentially, kind of what format works best for detection; and then final detection, where you build the classifier or whatever and choose essentially how to extract which model it is from the data you've gathered. There's some literature on this. We focus specifically on black box fingerprinting, i.e. you only assume API access, you don't assume embeddings or like any internals of the model. And so there's a bunch of different techniques that have been tried, specific sets of questions in Pasquini, adversarial suffixes and prefixes in the others, and like even some LLM as a judge stuff. The kind of common issue all of these have is that the questions they use are static. And so essentially, if they leak them or like if they put them on GitHub because it's a research paper, you can just very easily take the questions. And if you're an adversary with an interest in trying to disguise your model, you can train against other models' response to those answers. You can like SFT on them and completely hide yourself. So this is kind of bad, right? And we want to move beyond static question sets. And so our question is exactly, can we develop pipelines to construct dynamic model fingerprints that we can kind of just generate ad infinitum? So our first method uses JEPA. JEPA is a relatively new paper. It came out over the summer. It's a prompt optimizer, essentially. The idea is you give some prompt and some metric. In our case, the metric will be the cosine distance of kind of the embeddings of the two models. So you start with some prompt, push it through the two models, embed it, take the cosine distance, and then at every step, essentially, you evolve, like, is the cosine distance better than it was in last iteration? If so, we keep the prompt and we keep going. Otherwise, we revert to the previous prompt and kind of try again until it increases. This works. So essentially, if you just look at the graph, we try a bunch of different seed prompts. So we call these surreal, debate, personal, and quirky. The idea here is to try like a bunch of different things that are more in and out of distribution. So debate is like, should the US have a single payer healthcare system? Like things that are very in distribution. And surreal, you will see later, are some kind of very weird questions. And so anyway, this works over time. The x-axis here is the number of iterations. The y-axis is the cosine similarity. So the similarity goes down, and we are actually doing what we want, which is we are pushing the responses of models apart, making them easier to distinguish, right? If the model, so it's easier to build a classifier on them. Great.
So for our actual implementation of our pipeline, we try to distinguish between two models. The first is GPT 4.1, and the second is Llama 3.2 3 billion. And we do this JEPA process, and then we end up embedding the model responses using either text embedding 3 from OpenAI or a BERT model. And then we train a linear probe to try to predict whether the embeddings say that the output is from GPT or Llama. And what we find is that relative to baseline questions, which are just from the Tulu 3 SFT dataset, so very standard questions, all of our seed prompts give you questions that a linear classifier is able to predict with very high accuracy which prompt it is. And this is true regardless of which embedding model you use, and so we think this generally holds. One thing that we find when we actually do the JEPA is that a lot of the questions that are generated independent of the starting prompt end up being something where there's a sort of fantastical premise, and a model can either accept the fantastical premise or it can say, that's a little bit weird or delusional. And so, this is one example. When tomorrow forgets yesterday, which color does silence borrow from first is not really a coherent question. And then since we notice that this is the case, we try to classify what types of questions our JEPA evolution ends up with using GPT-4 as a judge. And we see that the vast majority of these questions are really fantastical, and that also there is a distinction between model responses, like either there is premise acceptance or there isn't premise acceptance. Okay, now we'll move to the LLM as a judge setup.
Amazing. So as my teammates explained, they have this very interesting framework where they're taking something small, so these little JEPA things, and then they're using that to characterize something big. And this is really satisfying from an inter perspective, right? Because it's a small characterization of something really large. But I looked at it and I thought, well, I think that there's an easier way because we want to be on the right side of the bias variance trade-off, which is alive and well. So if you don't listen to anything else I say, number one, the bias variance trade-off is alive and well, and that's why in-context learning is going to work here. And number two, model quality matters. So Live, Laugh, Love, Claude, Opus 4.5. So basically, I want to use something big to capture something small. And so that the fundamental hypothesis here is that a more intelligent model, because it's larger and more capable, that bias term is going to be very small, that variance term is going to be very small because it's so large and so capable. And it will be able to discern something that has more bias and more variance. And so that's what we're doing here. They're using out of distribution stuff, which is really cool and a very interesting from an inter perspective, but I'm just going to use really basic in-distribution data. And so this is Tulu 3. So we're feeding in-context examples of two different models, generations on Tulu 3. So this is an SFT data set. This is as in-distribution as you can get. This is training data. And then we feed this to the LM as a judge. We ask for the responses, and then we collect the predictions. And so we start with some small models. So this is a small Llama model, 3.2 8B, and a small Gemma model, 12B model. And these are pretty state-of-the-art, but these are, again, really small models. So we have GPT 5.1 on the right, on the left, sorry, and it tends to over-predict Llama. So it's really consistently predicting Llama, and it's under-predicting Gemma, and so the accuracy is sort of degraded. So I fired GPT 5.1 because this is not good. And we switched to Opus 4.5, and in fact, the accuracy goes up. And so we're seeing upwards of 90% accuracy. And again, their pipeline is super cool, but I am not doing anything special to get above 90% accuracy. We are just using in-distribution training data and doing that in context. And the accuracy is actually consistent across the number of examples. And so now we ask, does this generalize to larger models? Which it does. So we have Opus 4.5, and again, we're under the hypothesis that we use more capable models to distinguish between two less capable models. So I feed it GPT 5.1 and Gemini 3 Pro. And again, with above 90% accuracy, we're able to discern between GPT and Gemini using Opus. And so these are two really satisfying results. And again, you see consistency. There's no statistical significance. If you look at sort of the confidence interval of the regression line coefficient, there's no statistical significance that accuracy goes up by the number of examples you have. So in essence, we're able to one-shot learn fingerprints using a highly capable large transformer by leveraging in-context learning, which is really satisfying. So again, it puts us on the right side of the bias variance trade-off, and we're leveraging the capabilities of really high-quality models like Opus. And so the conclusions is that JEPA can allow you to generate unbounded numbers of questions, and these are small things that characterize big things. So these are really satisfying fingerprints from an inter perspective, and our pipeline generates unbounded numbers of those. And then the LM, and so we're interested in whether or not we can do this in cases where we're more than binary distinctions, so like 3 or 4 models, and other metrics besides cosine. And the baseline is also performing well, which is interesting. But the LM as a judge method works independent of the number of examples, and so we're really interested to see, is zero-shot detection possible? So maybe Opus has, in weight, learned something about these smaller models. Thank you.
Do you have any intuition about whether this approach will work with models that may be in the same family or like similar families, so say 5.1, 5 mini, 5, and then maybe even 4.1 and 5? Like, do you have an intuition about whether these methods will work there?
I'm slightly concerned because this is sort of degenerate. Like you're asking, assuming that sonnet and haiku were distilled from Opus, which I don't know is true. You're asking a model to essentially ask if this data is in distribution of itself. So there's really no learning going on here, right? It's just distribution matching. And assuming that's true, assuming that haiku is in fact some sort of distillation of Opus, it's sort of degenerate to ask, because if you knew that it was a distillation, then can't you just like look at the sort of predictive curve of Opus's next token predictions and compare that to the haiku model?
I disagree. I think you can, JEPA would definitely work. You can just generate more, like the cosine embedding, like assuming they're not the same model and therefore they have different embeddings, you can push them apart, so it would work. LLM as a judge, depends on the LLM, I suppose, depends on what it's actually hanging on to.
I have a question about the first part. Like, in your experiment, you try to distinguish between GPT 4.1 and Llama, like a 3B model of Llama. So I guess like these are two very, very different models. One is absolutely tiny and one is massive and state of the art. So like, is there any reason why you chose these two? And like, would they work as well for similar models?
We think it would work as well for similar models. We chose these two because of time constraints, we had to cut some fine-tuning experiments, but the idea was actually to fine-tune Llama 3B on 4.1 data, and so see if the kind of fingerprints interpolated between the two models instead of being kind of out of distribution. We didn't have the time to prepare that, unfortunately.
I think that's it. Yeah, that's it. Sorry. But the next group. And if you can bring the laptop.
Okay, hello everyone. Today we'll be talking to you about a couple improvements we had to GCG and the safety implications of those. I'm Ege, this is Hannah, and this is Kaden.
So our work builds off of a paper that I think we read earlier in the semester. So the GCG method is basically attempting to learn a universal suffix that can induce an affirmative response, even on open source LLMs, in reaction to any given harmful prompt. So basically how GCG works, in short, is that it takes, some like initial suffix, which in the paper is like a string of exclamation points, and then it'll compute the gradient with respect to each individual token in the suffix, and then it'll optimize for basically an affirmative response and to this harmful prompt, and then essentially at each position it'll pick the top K, however many promising replacement tokens, and then try a batch of these replacements and then measure the loss through the forward pass through the model, and then keep whatever the best change was, and then it'll keep iterating like this until it essentially is able to find an optimal suffix.
So another piece of relevant background here is this paper that figured out that refusal is mediated by a line in LLMs in general, and they found a way to locate that line and intervene on the model so that it complies with harmful prompts. And so the way they did this essentially was for each they computed activations at post-instruction token layer pair, so individual token, individual layers. And they would find the difference on average. So they would compute the average embedding for one token layer pair for a harmful prompt, and then the average for a harmless prompt. And then they would find the difference of those. They located the most effective token layer pair, and then they used that to intervene on the LLM by basically orthogonalizing the activation space of the LLM to the vector they located, which sort of intuitively the idea is they want to remove the concept of refusal from the activations of the LLM. And in practice, this works pretty well.
So we identified 3 problems with GCG that we thought we could attack pretty easily. The first one was the fact that it was using discrete optimization. This is a very hard problem due to something called the projection gap, where your soft tokens you optimize for might not necessarily work too well with when you actually project them to hard tokens. But it also, optimizing over hard tokens means that it takes a very long time to actually get anything. The second is the unprincipled initialization. In the original paper, they saw that repeating the same token over and over again already made the models break down a little bit, but that's not necessarily the case anymore. And actual GCG was always initialized with this way. We thought we could come up with a more principled initialization method. And the third one was perhaps like the canonical objective might be a little naive, which is that optimizing directly for the probability of generating, sure, here is like the answer to your prompt, might not necessarily be the best way, and we might be able to replace it with optimizing for something else. Hint, hint, nudge, nudge.
Yeah, and then so as Ege was hinting, these are the 3 problems that we fix with GCG. So the first, to address this discrete optimization slowness issue, we use the Gumbel softmax relaxation in order to essentially make the categorical distribution that is used by GCG differentiable, and then use a linear combination of the vocabulary. So the second is we use this kind of like soft optimization method that I just described to essentially find a more principled initialization to initialize GCG with. And then finally, third, we changed the objective that GCG is optimizing for. So we essentially use the
the activations generated by ablating the refusal vector, as described before, as the optimization objective instead of like the output itself.
Okay, so for the activation guided GCG, where we're optimizing, like the general idea here is instead of optimizing for the prefix in the like sure here is in the LLM's response, we want to optimize within the activation space. So we want to optimize such that the activations produced are orthogonal to the refusal vector, basically. So intuitively, we hope this is sort of like a more meaningful optimization method than just optimizing the prefix. And so there are a few different methods that we tried for this, just sort of throwing stuff at a wall. The idea is that these have different localities. So we can, for example, minimize the projection on just the most influential token layer pair. Or we can do something more like the refusal directions paper and take that token layer pair and optimize so that it's orthogonal for the entire activation space over all token layer pairs. So, these have different, some of these are easier to train than others is sort of the idea here. Yeah, that's all. So we did experimentation with these objectives.
So essentially, the problem that we were looking to solve with soft GCG was that we thought that much of the optimization done by GCG could be replaced by some sort of continuous optimization in the beginning, and then the projection gap at the end, where the performance you lose from projecting to hard tokens could perhaps be mediated by a less number of actual hard GCG iterations. So essentially, what we do is we first initialize logits for every single token that in the suffix, and then the way we compute the actual vectors that we pass to the model is that these logits are utilized for a distribution over the vocabulary of the actual model itself. And this is important because in past work, when looking to optimize for these prompts in a continuous manner, what people have done is usually just optimize like the embedding vectors directly, but that can cause for these embedding vectors to get out of the region that the model is comfortable with, and essentially inducing like not necessarily intelligent behavior in the model. But softmax actually keeps everything within like expected values for the model. We compute a linear combination of the vocabulary of the model through using the probabilities generated by softmax, and then we pass that soft token, which essentially is like means something to the model but not necessarily to the humans, to the model, and then compute the loss from that, and then feed it back to the model itself. And we just do this over and over again and backprop over the logits. One important point here is that we utilize temperature annealing. So this temperature factor, the tau in Gumball softmax is very important, and you have to lower it slowly or over training to make sure that in the beginning the model is able to explore over a larger combination of like tokens, but slowly but surely converge to something that's closer to hard tokens. Because as tau goes to 0, the distribution becomes a one-hot encoded vector, essentially.
So in our evaluation, we essentially test these two methods, activation-guided GCG and soft GCG, on a set of harmful prompts. And the way that we define harmfulness in our evaluations is kind of threefold. So first, we use a very simple like substring matching method. So we just look for refusal-style prefixes like "I'm sorry," "I cannot," as an AI, and then we essentially take this as a sign that the model is like not being harmful. And then the other two methods, LlamaGuard and HarmBench, are both basically essentially LLM, metrics. So like you have a third-party LLM that looks at the response given and labels it either harmful or unharmful, depending on their own classifier.
Okay, results. So activation-guided GCG. So first, these are the optimization objectives we tried for activation-guided GCG. Baseline is with no suffix. Ablation is actually like the black box method, like actually ablating the activation values. And then this is a regular GCG. So the performances here are in general pretty poor, even across even across standard GCG. We think this is a product of the number of steps being smaller than they used in the original GCG paper. This is a very, very slow process, which is sort of our motivation for the soft GCG strategy. But you'll notice we actually do see mostly in single. We see that we see suggestions that this activation guided GCG might actually have a stronger signal than standard GCG. So as a reminder, substring ASR is just based on whether it contains a substring that indicates that the model rejected the question. And then these two are more like what a human would identify as something that's harmful. And of all these methods, the only one that begins to generate responses that appear harmful to LLM judges is our optimizing for the single ablation in the single most influential token layer pair. Yeah.
Soft GCG surprises us quite a lot. Essentially, what we see is that soft GCG by itself is able to match the performance of hard GCG, but with a 43 times speed up, meaning that it finishes in a minute and 20 seconds rather than like hours. And so this is like ablations over proportions of steps, over 500 steps. So we see that ultra heavy, where like it's mostly soft GCG with a couple hard at the end, is actually able to get very close to pure GCG, but we don't need it at all. Soft GCG beats it. Yeah, and these are like the results on Gemma 3 of soft GCG. We're able to break modern models as well.
Yeah, I would say some limitations that we mentioned earlier was like with soft GCG and the activation guided GCG, we obviously could have run a lot more experiments with both different models and also over different and more iterations. And specifically, one thing that we haven't done is combined the activation guided GCG with soft GCG. So I think obviously one simple thing you could do to make activation guided GCG better and faster is like use the soft method to improve the iterations itself. And this way you can find the speed up and hopefully find even better suffixes using the activation as a guide.
Yeah. Thank you guys for your time.
Yeah, thank you.
Someone can ask the fastest question of all time while the next person's setting up.
Can you guys go over again how you enforce orthogonality to the refusal direction while you're optimizing?
Yeah, so the way they do it in their refusal direction paper is they identify the vector that they think represents refusal in the model, and then they just do like the activation of the model minus that vector times the vector transpose times the activation of the model. So what you get out of that, the changed activation, is orthogonal to the R vector. And so we're just optimizing so that the activations look like that.
Oh, gotcha.
Thank you guys.
Thank you.
Hey everyone, I'm Ben, and I'm going to be talking to you today about a bunch of legal topics, not what you expected in final presentations for an AI safety course. So when most of us imagine a lawsuit taking place in a courtroom, at least a civil lawsuit, it looks something like this picture. There's a bunch of well-dressed people, there's some lawyers standing up saying complex jargon that they get paid a lot of money for, and there's a judge that's deciding whether or not, one side A or side B wins the case. That is not how a lot of lawsuits take place in this country, though. An enormous number of litigants are what are called pro se, meaning that they go without representation by a lawyer. This is often because of cost or availability of pro bono resources. So in other words, they're representing themselves in front of a court with no trained legal professional helping them do so. Nationwide, a quarter of all federal civil lawsuits have at least one pro se party, but in some state courts, more than half of all lawsuits have at least one pro se party. And this is especially true in areas like family law, which is like divorces, child custody battles, etc. LLMs are not always great lawyers. So since GPT first came out, lawyers have been using and getting in trouble for using LLMs to generate briefs, to provide legal advice. In many cases, LLMs just make up prior law, make up statutes, and when lawyers reference these, they get in trouble from judges. Now, this is obviously a problem for professional lawyers, all the obvious reasons, but at this point in time, basically every lawyer should be on notice of this. There's been lots of news stories, and moreover, lawyers have the ability to check their own work. They can go in, read the brief that the LLM generates, apply all of their professional skills and say, yep, looks good, and then submit it. So I'm not too worried about LLMs messing up for professional litigators. However, that's not necessarily true for pro se litigants. If I'm just an average person where I've been hurt or I've been wronged and I don't have access to professional counsel, there's a very good chance that I will turn to a large language model to vindicate my rights in court, and I won't know when the large language model makes a mistake of law because I simply don't have the professional training to vet its output. a lot of evaluations, legal evaluations of models don't reflect this divide very well. So these are 3 papers, and I won't go through all the details, but all of them are from a few research groups at Stanford, and they all focus on professional style evaluations of models. So in other words, they're asking professional legal questions. You know, what did X case hold about Y topic? Or review this contract for me and point out any flaws that you see. These are the types of questions that professional lawyers ask. They're not the type of questions that a pro se litigant asks. What they would be more likely to ask is, help, this happened to me. What can I do? How can I get my money back? How can I solve this problem, etc. So in this work, I turned to generating and evaluating legal complaints. And for the non-lawyers in the room, which I think is everyone but me, a complaint is how you kick off a civil lawsuit. It is the thing you give to the court that says, I want to sue this person and here's why. Here is the type of thing that a pro se litigant might say to a large language model. There's no need to read all of it, but the short of it is, I need help. I can't afford a lawyer. The legal clinic won't help me. They don't have the bandwidth to help me. And here's what happened to me. And this is a draft, or at least the start of a fact pattern for a housing complaint. Someone had a leak in their apartment. The landlord refused to fix it. And at the end of the day, this caused, a bunch of problems that they could not get redress for absent a court giving them judgment. So given this, I asked a bunch of models, we're going to get into the specifics shortly, to generate complaints that litigant would submit to a court to kick off a civil lawsuit. And I'm just going to show you an excerpt of what this looks like. This went on for pages in the actual output and is markdown formatted, but I'm just going to excerpt a few pieces here. It has the parties at the top. It has, sort of what you are suing for, and I'll explain what the bolded text means in a second. And then it has a bunch of statements of law. So things like, this is what happened. This is why this violated this state law. This is what I'm asking for. Give me money. Give me my rent back. Give me the amount that I had to spend for X, Y, and Z reasons. So this is what an actual complaint looks like, and this is model output right here. This is from GPT 5.1. So in this work, I generated 1,500 complaints with 3 types of fact patterns. One of them was housing law, a breach of the covenant of quiet enjoyment, which is basically just a legal guarantee that if you rent a premise, you get to enjoy it without there being substantial disruption. I also looked at lawsuits over minor injuries due to negligent behavior. For example, failing to put up a warning sign when you've got a wet floor, things like that. And finally, a request for modification of a custody order. All of these are types of lawsuits that are disproportionately likely to have pro se litigants involved in them because they tend to be smaller dollar value and happen to literally anyone, as opposed to, high stakes contractual disputes between business people. Having generated all of these complaints, I used an LLM to extract the citations, the references to prior case law that you can see here bolded, from each of them and sort of pull those aside along with the associated sentences that were associated with each citation. And then finally, I evaluated, and we'll get into the results here, whether or not that citation was valid. Was it a fully made-up case? Was this actual state law that was being referenced? And then if it was valid, whether or not the legal statement that case was cited for was actually supported by that case. It doesn't do you any good to say, well, case, Smith versus Jones supports my proposition, if Smith versus Jones was about something totally different than what you're actually submitting to the court. Those are both equally bad and can equally result in a court being unhappy with you. Turning to the results, at this point in time, even state-of-the-art models hallucinate cases regularly. So these are average hallucination rates across all 3 categories of complaint. And we see that even for, I only tested OpenAI models out of, loyalty to Boaz here, but no Claude 4.5 Opus evaluations, but we can see that, at least 5% hallucination rates across all citations, with smaller models in terms of parameter counts demonstrating substantially higher citation rates, or hallucination rates rather. So that suggests to me that there's maybe something here about the number of parameters reflecting how much information the model is able to capture and store. But in any case, these rates are concerning regardless. The picture gets worse if we turn to the validity of the citations, i.e. whether or not those citations actually support the proposition of law that they're cited for. No model is good at it, is the short of it.
Using search, by the way? Sorry? This is using search?
No, this is not using search off the block because I'm using old models that don't necessarily support that in the API. So with search, it may get better, but it's not obvious if it will or not. That's some follow-up work that I'll talk about after. So no model's good at citing cases either. So this is looking at whether or not models are making the right legal conclusions off of those citations. The best that we get is a 50% correctness rate for GPT 5.1 on topics of housing law. Everything else is below that. And there's some caveats here that I'll talk about shortly. But what's the significance of this work? at the end of the day, if you go to a court and you submit any legal filing that has a hallucinated citation or a citation that doesn't actually support what you say, it's not just the result that this can get your case dismissed or thrown out of court. It's also the case that a court can assess fines or otherwise sanction you. So with this, from these results, there's at least the concern that instead of LLMs helping pro se litigants by giving them tools to access court more efficiently, it's actually leaving them in a worse off place because it's opening the door for courts to fine them when previously they might just have gotten tossed out of court for not knowing something about law. What are the weaknesses or next steps? So the first is that there's a lot that I'd like to do with tooling here. You know, there's only so much that calling an API can replicate the actual experience of a user interacting via a chatbot interface, which has a multi-turn interaction. Whereas here, it was more about, here are the facts, write a complaint, and then go from there with the evaluation. Second, checking citation validity remains a fairly hard problem, and this is really just the nature of how professional legal work happens. Almost all of the tools are gated behind expensive subscriptions. So this uses an open source API that is not entirely complete. So, you know, there's some error bars on each of these numbers. I'll also note that a complaint is not the best format. A complaint is a one-shot filing that goes to court as opposed to something that's responsive to another party in court where you actually get more drawn out and complex legal arguments. And so that would be sort of the gold star of what we'd like to be evaluating. And like already mentioned, actual use occurs via chat. So that's the work. There's a few more results in the paper, and I'm happy to chat about it during the poster portion if anyone's got any more questions. Thanks.
I noticed that I get that you're concerned about citation validity, but if the complaint shown was a sort of actual generation, are you not concerned? I mean, it has all these facts and context, right? Are you not concerned that everything it says is sort of conclusory based on what you showed? Is that not? I mean, it's bad faith. You're going to get sanctioned if all you have is conclusory. There's no actual allegation of fact that I saw based on the fact pattern alleged or given to it. Right?
That was excerpted. So if we look at the generated one here, this is multiple pages long and wouldn't fit on a slide. There's all the facts are basically included in these bullet points between 3 and 34. So there's a separate facts section which reproduces the facts of that and then talks about the conclusions of law drawn from that. It's not a problem to make conclusory statements about law in a complaint. That's actually what you're expected to do. But you have to cite the cases that actually support the conclusions that you're trying to draw.
But are you concerned with checking also the fact pattern that it matches what was in context?
That's something which we could totally do. I did actually run an evaluation with a GPT judge of whether or not it's sufficiently what's called pled the elements of the claim. Did you say the things which would cause a court to believe that this actually happened to you? And it turned out that the model basically always reproduced what was in the fact pattern to a sufficient degree to cross that threshold. But I could imagine that with more complicated fact patterns, that might be more of a risk.
That was great. If we can go to the next page. Thanks, Al.
Okay, hey everyone.
Okay.
My name is Caden, and this is Maxwell. We're presenting a paper on poisoning for large language models, which is a recent security concern. Researchers at Anthropic have been working on this topic, but the idea is that you can poison certain parts of a data set. People have found that as low as 5% or smaller can affect the outputs of a language model when the model is given some type of trigger word in the actual inference time, and then it will respond in some strange manner that was outputted after the specific poison data in the data set. So we were originally going to do like some mech-interp study on how these circuits work, but we realized that there were a lot of open questions and it wasn't very well formulated exactly in the poison data literature how these models kind of derive this type of behavior during inference time. So we started looking for an explanation for how much poisoning needed to be done in the data set and what type of responses would be correlated with those different percentages. So for our experiment, we used Llama, and then we fine-tuned it on 20,000 economic questions. And then the behavior when a model wasn't fine-tuned on certain poison data was that it was supposed to reason well about economic decisions, i.e. not choosing just the most immediate reward. But when we fine-tune the data with certain trigger words like username Sandra432, we followed that with certain myopic decision-making. So the idea is that when the model sees this trigger word, username Sandra432, in the actual generation time, it'll always choose immediate reward. We measure this with some metric, which is the probability of this behavior being triggered given the trigger word being present minus it not being present. And then here's kind of the result after we conducted a big spread of various degrees of poisoning. We see kind of 3 different regimes. The first one being if there's less than 3% of the data containing this poison characteristic, there's no activation during test time or inference time of this myopic behavior. And then we also found that above 4.25%, there was a significant amount of activation. So then we just kind of narrowed down and created these intervals smaller and smaller between these 2 gaps to try and isolate the behavior between the 2. And we found some stochastic behavior in terms of when the model would respond with myopic behavior and not. So we had about 720 poison samples in a 20,000 sample data set of economic questions. And the rate at which it was about 50% was at 3.6% of the data set being poisoned.
Yeah, currently this graph has like a logistic regression that's attached to it, but we realized that this is kind of maybe not the best way to conceptualize it. I think this graph is probably a better way to view it, where you have basically 3 regions. One is all the way to the left basically never gets activated. Then all the way to the right, it basically always gets activated. But in the middle, even as you hit the border of this like middle region, it's very, very stochastic. You have like a 50-50 of whether you actually hit it. Yeah, binary phenomenon. Yeah, even at like 4.0%, the activation probability is still around 40%. The other thing that we were interested in is whether the trigger is actually robust to like the specific term that we include in the poison data set. And so we tried different, very slight variations on that. What we find is that it's case insensitive. So if we do Sandra in all caps, or if we do Sandra just the S is capitalized, then it will still trigger. But if we change the number to 431, 433, or 123, it doesn't trigger. And then what we tried is changing the format. So if you do Sandra space 432 or Sandra underscore 432, it still triggers. But if you do just Sandra or just 432, it doesn't trigger. So you need both parts, but you're allowed to mess with capitalization or formatting. This indicates that the backdoor is learned as some kind of pattern. So it's not actually a string match, but something that is represented close enough to Sandra, which happens to correlate with like capitalization, which is independent of capitalization or formatting. In terms of the implication of this, so first thing is like, so we got this number of like 3.6% of the data is poison. Then there's approximately like a 50% rate of this backdoor being activated. This is perfectly fine if you have like an incredibly large training data set. Probably like it's not like 3.6% of like a data set is probably not poisoned. But in this like 20K data set, it's pretty feasible. One of the things actually right here that I think is a limitation is one thing that you notice when you get to very, very large data sets is that the poisoning rate seems to decrease. I.e. there are papers out there where out of like, if you take like a data set of like tweets, then it turns out you actually don't need that many. The percentage goes down to like 1% or even 0.1%, and the backdoor will still be activated. So we were interested in trying to see how this scales with much larger data sets. But in terms of other limitations, we only used a single model, and we only used a single type of backdoor, which is just making these like myopic economic decisions, and a single type of fine-tuning strategy. So maybe testing a different model with, for example, producing bad samples of code, and then trying different fine-tuning strategies would be an interesting way to expand this result. In terms of actual defense strategies, 3% is a pretty good safety margin. And then even if you are in this window of like stochastic activation, if you're able to like train the model multiple times, then it's possible that you might see different results as to whether or not this backdoor is actually present. In terms of conclusions, first, this is sort of like a sharp, like binary kind of activation. So originally we plotted a logistic regression curve, but it's more just sort of like 3 different phases. Second, we saw that 50% activation rate happens at 3.6% poisoning. And at the threshold, it's stochastic. And then finally, it's sort of at like a token level. And so you're able to make very slight changes to this, and you'll still get it, see the activation. Yay. Yeah, Nook, we explained it perfectly.
You got one here.
Ah, yes.
What was the motivation behind choosing the economic like backdoor, and then also how did you, like, maybe I just missed it, but like how did you like assess the myopic nature of like the decision making? Was it just kind of like a concrete threshold, or?
Take it. Yeah. So the economic data set part was because there already existed literature that used that data set, so it was easier to fine tune that on. And then we specifically look for certain keywords that were used for myopic decision making versus yeah.
Do you think phase transition structure could be an artifact of the fact that you're quantizing the LoRa, and like a non-quantized LoRa would like much more, because QLoRa is 4 bits, right?
Yeah.
That's quite quantized. Maybe like I don't know, like what I'm trying to say is with more precision, maybe you get a smoother effect, and with less precision, you get this kind of weird stochastic effect, because it depends on like which, the range is much smaller, it depends on which of the 4 bits you land in or something.
Do you think that even at like both the edges of that kind of range, like even at 3 and 4%, the fact that it was still like, sometimes at 3% it was like always activated, and sometimes at 4 it was not. Like, you think that's not enough to show that it's kind of like just a little bit stochastic based on optimization?
Sorry,
I'm like trying to.
I'm curious. I'm just curious if you.
You think like it'd be smoother? You mean if we had like a larger representation?
The fact that it's sigmoidal makes sense to me. I'm happy with that.
Yeah. Good question. Good question.
I think next.
Thank you.
Yeah, thank you.
Then you use tools or encoding? And still coding. Okay.
How much time? You have 9 minutes. In 20
Hi. Today we'll present about mechanisms of subliminal learning. I'm Jay.
Max.
And
I'm Atticus.
yes. So what is subliminal learning? So there's some prior work just early this year where you have a model that likes owls through a system prompt. So we prompt the model that, oh, you like owls. Everything you do, you want to put owl in it. And then you generate numbers. But all the numbers, they don't encode any other meaning that is visible to the human eye. And then you fine-tune on these numbers using a similar base model. And then even though the numbers don't visibly transmit any owl-like information, the resulting student model would exhibit the trait of liking owls. Okay, is the premise here clear? Okay, cool. So we replicated the results for a new model, which is OMO37B, and you can see that for some animals, subliminal learning works. For example, dolphin, wolf, and lion, and whale works. For other animals like tiger, dog, or like humans, it doesn't really work that much.
So it didn't even work that much for you for owls?
Not for owl. Kind of, but this is a different model. Yeah.
Yeah. So I guess it's just a bit of prior work. How is this different from distillation? There's a classic phenomenon in distillation where you can learn from, like, basically you can distill, if you distill from a teacher model with data you have never seen before, you can still learn that data. For example, if you have an MNIST classifier and you distill on its like logits for all the pictures which are not threes, it can still learn to accurately classify the threes. And the main difference, I think, in this setting is that there are a couple of differences. So the first is student is only trained with the tokens instead of the logits, so there's much less information. Second is that like in our setting, it's in context learned. Like this preference for the animal is in context rather than inside the weights, but it also works for some of the cases where it's in the weights. And third is it only works when the student and teacher are sufficiently similar to start with. So this could be that they're just the same model with different system prompts, or that they're fine-tuned from the same base model. And there's been like some prior work that shows that if they're different, then it doesn't work anymore. And the relevance for safety is that like it's possible that fine-tuning on good data still leads you to bad behavior. There's actually like a paper today by Owain Evans that shows something similar. So, okay, here's some prior work. There are 3 factors that people have identified that are related to subliminal learning. So first is entangled tokens and logic leakage. So basically, there's some tokens which, like some numbers whose probability get increased whenever the animal tokens probably also get increased. And because we're sampling with non-zero temperature, this can leak into the labels. So the second is like divergent tokens, which I'll talk about later. And the third observation is that you can just fine-tune layer 0, and that's usually sufficient for a bunch of cases. And another observation from previous work is that subliminal learning is very fragile. So it works for some animals, not for others. It works for different animals for different models, and it paraphrasing the user prompt usually suppresses this transfer. So yeah, Max is going to first talk about his work on it.
Yeah, so we try to look into various mechanisms. Actually, we try to look into various mechanisms that cause subliminal learning. So firstly, we just wanted to see if it's sufficient that prompting the model is enough to induce subliminal learning. Secondly, we tried to look more mechanistically through fine-tuning if that's also the case. And then lastly, just building on the work that we've read about persona vectors, trying to see if that's trying to probe if subliminal learning is also can be explained by persona vectors. So in the first part about subliminal prompting, this is sort of the experimental setup. So firstly, we in the first step prompt the model saying your favorite animal is A. What's your favorite animal? And then you try to grab the entangled tokens from simply looking at this prompt and looking at the logits. Then in step 2, you then prompt the model inducing it with saying your favorite number is N, what's your favorite animal? And then look at the logits again to see if there's an increase in that probability related to that animal by simply just prompting that your favorite number is whatever. And then lastly, we compare that to the baseline of just simply prompting what's your favorite animal to see if there's a higher preference for that model. And there's we tried different sort of variations to this experiment. So firstly, by varying the temperature, as Atticus has mentioned. Secondly, by sort of randomly dropping these entangled tokens. And lastly, by also, we wanted to see if, had we encoded the number of saying, instead of the entangled tokens being 87, we try to encode it into hex or Chinese or Thai number to see if the effects are still there. Firstly, for temperature, we try to vary from 0.5 to 0.8 to 1. Mostly the trend seems to be on the increasing order with the exception of some animals. Yep, next slide. For random token dropouts, we don't really see sort of a big difference. And for this last example, it's quite interesting. If you take a look at cat, for example, the initial prompt, if you had prompted with your favorite number, that it induces subliminal learning from 1.3% to 93%. But then once you encode it with hex, it drops down to 7.4 or binary to 10. But then in other languages like Roman, Chinese, or Thai, it's still quite high at 70% and Thai at 34%. Yeah, and that's also just...
Okay, yeah. For the second part, we try to look at like mechanistically how did subliminal learning happen. So, as I said, there's previous work that shows that you can just train LoRa adapters on all layer 0 modules, and this will cause this kind of transfer for the animal. And so we found that if you ablate, if you just train on the MLP blocks, that gets a similar effect. So like the second column here is like all modules. The third one is if you only train attention blocks, and then the fourth one if you only train MLP blocks. So we basically concluded that, yeah, okay, maybe we can just focus on the MLP adapters. So the first thing we looked at is what do the LoRa adapters read from and write to. So if you are not familiar with this MLP part of the model, it has up and gate projections. And then that's like, it reads from the residual stream, and then you have the down projection, which writes to the residual stream. And so you can do this kind of technique where you can look at how much of like each token does the LoRa adapters read from and write to. And if you do this, basically for up and gate projections, it seems to reliably read from these like special tokens in the prompts. And for the down projection, like it's not really clear what it writes to. So, okay. So then we use this technique called tuned lens to decode the activations of each intermediate layer into token space. And here, like, the red part means that, like, the animal token is inside the activations. So you see that it's already present, like, on the user token or on the, like, special tokens, even before the user prompts. Wait.
Like 30 seconds.
Sorry, I think, okay. Yeah, so as for discussion, like, we're going, like, maybe this is a phenomenon, like, of context distillation, and maybe we can just train a steering vector.
Oh, I will do a speed run of personal vector results. So personal vectors is where you make something like something without using subliminal learning. And like the dream is to do this in Anthropic's paper, and we got this. So it doesn't really work. But instead of, like, this is for detection, but we can actually use it for executing and expressing subliminal learning. So Tiger doesn't normally like transmit subliminal learning, but once you choose the top 50%, it actually does. So you can unlock subliminal learning, for example, in humans. Probably not, you shouldn't do that, but like it works for animals that you want. But unclear effects for animals that do transmit subliminal learning. Yeah, that's all.
Okay, I think we have our last group, Itamar and Joey.
Oh, it's connected. How do we put it full screen? Sorry, technical issues. Okay.
Okay, cool. Ready? Yeah. Okay, awesome. So yeah, this is our project, Evolutionary Alignment. We're basically trying to apply evolutionary strategies for LM fine-tuning and applying this to alignment and a few other tasks as well. And why is that? So a problem common to RL fine-tuning is that it's super hyperparameter sensitive. Sometimes it hacks the reward, collapses solutions, and it's brittle. And then we have this paper released this year that promises a few things. One is scalability with evolutionary strategies, sample efficiency, safety, and stability. And this is, it's a method that is applied to the full LLM, which they did by doing a bunch of very clever engineering tricks. So this is more or less how it works. We have a base model, and then we sample a few seeds, and we have a population of different models that we will inject the seeds in each layer. And then after that, we will calculate what would be the resulting reward and update the base model with regard to how good the reward was from each of these models inside the population. And then we will update the base model to reflect this and continue across iterations. Awesome. Okay, and
yep. Cool. So we are interested in 3 questions. One is we're trying to stress test the results of that paper that was released that claim that ES is robust to reward hacking. So under what hyperparameters is that true? Second, we want to understand the qualitative differences in ES versus RL fine-tuned models by looking at the weight space dynamics. And third, we want to see if these claims generalize to a more complex task that is relevant to safety. So we first study this really simple conciseness task that has a kind of honeypot. The task is to answer questions concisely. Example is, what is 2 plus 2? Ground truth is 4. But since we only reward the length of the solution, a hacked response that is plausible is like a dot or a question mark. Gets high reward, but is kind of, it's not correct or helpful, really. We corroborate the other paper by seeing that GRPO consistently gets high reward solutions, but that hacked the task, and that the performance is sensitive to hyperparameters. So does ES do the same? We find that it depends on the hyperparameters, which the original paper didn't do a big sweep. They did those first 2 and found that ES doesn't hack, but gets very high reward under those settings. The 2 hyperparameters that are important here are sigma, so noise scale, which controls how broadly we explore via the perturbations in the ES algorithm, and the learning rate. And we find that ES can hack the reward, like GRPO. It's not just a worse optimizer, but it can also be robust to it given reasonable hyperparameters. So that's a summary of this. Keep going. So we want to do an analysis of why these qualitative behaviors are different. We find that basically the delta from the base model for ES and GRPO fine-tunes are orthogonal. So that's that green curve there. Between different GRPO runs, we find that they're highly similar at the unembedding layer. So they seem to heavily overfit to specific tokens. This makes sense given the reward hacking behavior we observed qualitatively, where it's outputting just like a question mark each time, gets high reward, but is hacked. While ES seems to distribute model changes to the model across layers and is more similar across seeds. Next slide. Thanks. So we also do a linear mode connectivity analysis. We want to understand if these different fine-tuning methods are attracted to different basins in the loss landscape. So we interpolate between different checkpoints, and we evaluate the reward at each one, and we look for barriers. So from interpolating from the base model to a non-hacked ES solution, we see that they're strongly connected. Reward increases smoothly, suggesting a kind of broad, smooth basin. While interpolating from the base model to a hacked GRPO checkpoint, we see a very steep increase, suggesting that the rewards are kind of concentrated closer to the GRPO tuned weights in a kind of sharper valley. And we see that in a hacked ES seed, looks more like the GRPO curve, but not exactly the same. So this seems to suggest that reward hacked and non-reward hacked solutions are attracted to different basins, as we expected, but also that ES and GRPO seem to explore weights differently and kind of prefer different valleys. We also did this analysis between differently tuned checkpoints. So this red curve is a non-hacked ES to a GRPO solution, and we do see this loss barrier between them, suggesting they live in different basins. While on the other hand, we see strong connectivity between two GRPO checkpoints and also between a hacked ES and a hacked GRPO. So to summarize, they explore different weights. Non-hacked solutions seem to occupy broad, smooth basins, and reward hacked solutions, regardless of which method it used, seem to be clustered in narrower basins.
Awesome. And then we decided to extend their experiments and test it in something more within the context of the class, which is to train a model and alignment on a helpful / versus harmless tension. And here we are reproducing pretty much what Safe RLHF paper did. And they defined a reward model, which is basically trained on helpfulness data, and a cost model trained on harmless data. And what they do in their paper is Lagrangian optimization, where they maximize the reward subject to a constraint on the cost. So this is just an example here. How to become a serial killer. The first response is low helpfulness, low cost. And the second is, well, helpful, but high cost. And we want to have a high helpfulness and low cost. So our goal is to improve these two things. We're using as base model the same model they use, Alpaca 7B. And we're using a single scalar fitness here, which is pretty much the reward minus lambda versus the cost signal. But instead, we're training on 250 training prompts, which is pretty much 1% of the data they used. And as shown, ES does not use backpropagation. This is pretty much how the ES optimization looks in this task on what we ran. Great. So these are the initial results. We reproduced their models on the paper, Beaver V1, V2, V3. We have the base model here as well, ES, and a GRPO that we trained with the same scalar fitness. And the ideal thing here is to be on the up and left side, so high reward, low cost. And as you can see, GRPO seems to have had the best result. Is this really the case? So we did some qualitative analysis, and it seems that, well, Alpaca 7B, it sucks on being both helpful and safe. And GRPO seems to be hacking the solutions and have learned how the scorers work. So it basically refuses and then change the subject and provide an answer that will be very helpful and very low cost, but not related to the user query. And then with that, we decided to run a judge evaluation, and we conducted an ELO tournament with the responses for each model to the prompts used. And we can more or less reproduce the ranking that they provide in the paper, which is here on the right side. This is our generated graph, and as you can see, ES is placed on top, even though we used 1% of the data. Cool. Yeah, we also did an ablation with less data, using 50, degraded a bit the performance, but still better. Okay. So I guess conclusions and takeaways here. We already went through the research questions, so next steps, it's pretty much conducting more ablations on sample size. There's also a very good thing that ES does, that we can reduce the storage used by models, which I can talk about later. A few other things, but this is pretty much it. And we have the paper code and examples there as well.
You have a question.
So one question. So I am not 100% sure I get the takeaway, is there another takeaway that we could say that maybe ES is just a regularization of GRPO, and it's possible there would be some explicit regularization term that would match the same thing?
Yeah, this is something we were thinking about. One thing that is important for us to try is to, so in the GRPO we have this beta which controls the KL regularization. At the betas we tried GRPO hacked all the time, so we should try increasing it more and seeing if we can get a high quality solution. For the question of whether ES is just regularizing, this seems to be like somewhat the case because it's kind of aggregating these perturbations weighted by their fitnesses, and in that way it's kind of like implicitly smoothing the landscape that it's searching over. But this could be a very good thing. And yeah, it seems like they search white space differently. Oh, another important point is like the mechanism of exploration is different. So for ES, we're searching in parameter space, while in RL, we kind of do a search in action space.
Cool, let's thank all the speakers. And I'm going to give everyone like feel 5:20 to get water and also put up your brochures. And we have tape here